At this very moment, you exist on a sphere of rock traveling through the void at speeds that would make the fastest jet fighter look stationary. This sphere circles a ball of hydrogen undergoing continuous nuclear detonation, a furnace so powerful it will burn for 10 billion years. That star belongs to a spiral collection of several hundred billion similar furnaces, all orbiting a supermassive singularity at the galaxy's heart. And that entire galactic system represents nothing more than a speck of dust in a room so large that calling it incomprehensible would be an understatement. What you're about to discover will permanently alter how you perceive reality itself. Consider the moon for a moment. That grey companion hovering in our sky sits roughly 240,000 miles from Earth. Humans have walked on its surface. We've left footprints, planted flags, and returned home with bags of lunar rock. The moon feels achievable, reachable, almost close. Now understand this. If you could drive a car to the moon at highway speeds, the journey would consume 6 months of continuous travel. No stops, no sleep. 6 months to reach the closest celestial body to Earth. This single fact should begin reshaping your intuition about cosmic distances, because the moon represents our immediate neighborhood, and already the scales involved exceed normal human experience. The Sun sits 93 million miles away from our planet. We call this distance 1 astronomical unit, and it serves as our first measuring stick for solar system dimensions. Light itself, moving at 186,000 miles every second, requires 8 minutes to bridge this gap. When you see the Sun, you're looking at where it was 8 minutes ago. The present position of our star remains unknowable to us in real time. This 8-minute delay means that if the Sun somehow vanished, we would continue seeing it, feeling its warmth, living as if nothing had changed for 8 full minutes before darkness and cold arrived. The universe operates on time delays we rarely contemplate during daily life. Neptune orbits at 30 astronomical units from the Sun, 30 times farther than Earth. Radio signals sent to spacecraft near Neptune take 4 hours to arrive. When mission controllers at NASA send commands to distant probes, they must wait 8 hours for a response. 4 hours for the signal to reach its destination, 4 more for confirmation to return. Conversations with robots exploring the outer solar system require the patience of geological processes. Real-time control becomes impossible. Every command must be sent with the understanding that conditions will have changed long before the response arrives. Yet Neptune resides in our cosmic backyard. The outer edge of the Oort cloud, that sphere of icy bodies surrounding our solar system, extends perhaps 1 light-year from the Sun. 1 light-year equals 6 trillion miles. At this distance, the Sun would appear as just another star, no brighter than the others dotting the night sky. Everything humans have ever built, every satellite and probe we've launched, every astronaut who's ventured into space has remained within a tiny bubble measuring less than 1/10,000th of 1 light-year across. We are infants who have barely crawled beyond the doorway of our home. The nearest star system, Alpha Centauri, lies 4.37 light-years away. This means light from that star, moving at maximum cosmic velocity, travels for more than 4 years before reaching Earth. In practical terms, this distance translates to roughly 25 trillion miles. Our fastest spacecraft, Voyager 1, currently traveling at 38,000 miles per hour relative to the Sun, would need more than 70,000 years to reach Alpha Centauri if it were heading in that direction. 70,000 years. Humans hadn't invented writing 70,000 years ago. We were still learning to make sophisticated stone tools. The timescales required for interstellar travel using conventional propulsion exceed the entire span of human civilization. 4 light-years of emptiness separate our Sun from its nearest neighbor. To visualize this void, imagine shrinking the Sun down to the size of a golf ball. At this scale, Earth becomes a grain of sand orbiting about 8 feet away. Neptune, at the edge of the planetary region, circles at about 240 feet. The Oort cloud extends perhaps 10,000 feet, roughly 2 miles. And the nearest other star, another golf ball, sits 350 miles away. The space between stars contains almost nothing, a vacuum more complete than anything we can create in laboratories on Earth. Stars are islands of matter floating in an ocean of emptiness. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. The uncertainty in this count comes from dust clouds that block our view of distant stellar regions, plus difficulties in detecting the smallest, dimmest red dwarf stars that actually comprise the majority of stellar populations. But even using the conservative estimate of 100 billion stars, the scale becomes staggering. If you could count one star per second without pausing, you would need more than 3,000 years to finish counting the stars in our galaxy alone. The Milky Way measures approximately 100,000 light-years from edge to edge. Light beginning a journey on one side of our galaxy won't reach the opposite edge until 100,000 years have elapsed. When we observe distant regions of our own galactic home, we see them as they existed when early humans were just beginning to migrate out of Africa. The galaxy we think we're observing doesn't actually exist in that configuration anymore. By the time light shows us a distant stellar neighborhood, tens of thousands of years have passed, and everything has moved, evolved, and changed. From our vantage point about 26,000 light-years from the galactic center, we orbit the core once every 230 million years. This means that since the Sun and Earth formed 4.6 billion years ago, we've completed roughly 20 orbits around the galaxy. During the age of dinosaurs, our solar system occupied a completely different region of the Milky Way. The constellations visible to the dinosaurs bore no resemblance to the patterns we see today. Stars drift through the galaxy like ships crossing an ocean, occasionally passing near each other, but mostly maintaining vast separations. The space between stars varies, but typical separations measure several light-years. In the densest regions near the galactic core, stars cluster more tightly, perhaps with neighbors only 1 or 2 light-years away. Out here in the spiral arms where we live, neighbors tend to be farther apart. This distribution means that despite containing hundreds of billions of stars, the galaxy consists mostly of vacuum. Matter represents rare exceptions scattered through an overwhelming void. We live in a universe that is far emptier than most people imagine. Now we must make a leap that will strain intuition beyond its breaking point. Everything described so far, every star in our galaxy, every nebula, every black hole, every planet orbiting every stellar furnace, all of it together represents one single galaxy, one unit, one grain of sand. Because observations have confirmed that our universe contains approximately 2 trillion galaxies within the observable region of space. 2 trillion separate collections of stars, each containing billions or hundreds of billions of stellar systems. The Andromeda galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. Photons leaving Andromeda right now won't reach Earth for 2.5 million years. When we observe Andromeda tonight, we see it as it existed when our Australopithecine ancestors were learning to walk upright in Africa. The galaxy we're looking at is ancient history, preserved in light that has crossed intergalactic space for millions of years. Andromeda contains over 1 trillion stars, more than double the Milky Way's population. If our galaxy is New York City, Andromeda represents the entire eastern half of the United States. Andromeda approaches us at roughly 250,000 miles per hour. This sounds alarming until you remember the distances involved. Even at this tremendous velocity, Andromeda won't reach us for another 4.5 billion years. When these two galaxies finally collide, the merger will take several billion years to complete. Stars within each galaxy remain so widely separated that stellar collisions will be extremely rare despite the galactic crash. Instead, gravity will reshape both spiral structures, ultimately forming a single elliptical galaxy. Our solar system will likely survive intact, flung into a new orbit around the merged galactic center. Between our galaxy and Andromeda stretches a void containing almost nothing. A few scattered gas clouds. Some dark matter we cannot directly detect. Temperatures in this intergalactic space hover just above absolute zero. Densities fall below anything achievable in vacuum chambers. The 2.5 million light-years separating our galactic homes represents the smallest step beyond our local cosmic environment. This distance defines the scale of our immediate galactic neighborhood, and already it exceeds human comprehension. Our galaxy doesn't drift alone through cosmic space. The Milky Way belongs to a collection called the Local Group, containing more than 50 individual galaxies bound together by mutual gravitational attraction. Most members of this group are dwarf galaxies, containing only a few billion stars each. These smaller systems orbit around the two dominant spiral galaxies, the Milky Way and Andromeda, following complex paths determined by the gravitational interplay between the two massive members. The large and small Magellanic Clouds represent the most prominent dwarf companions to our galaxy. Visible to the naked eye from southern hemisphere locations, these irregular galaxies orbit the Milky Way at distances of about 160,000 and 200,000 light-years. Our galaxy is slowly consuming these smaller neighbors. Tidal forces strip stars and gas from the Magellanic Clouds, feeding material into our galactic disk. This cosmic cannibalism has continued for billions of years, with our galaxy growing larger by devouring nearby systems. The Local Group spans roughly 10 million light-years in diameter. Despite this enormous size, it represents just one gravitational family among millions of similar groups scattered throughout cosmic space. Galaxy groups and clusters represent the standard organizational units of the universe. Isolated galaxies are actually quite rare. Most galaxies exist as members of larger gravitational communities. The nearest major galaxy cluster, called Virgo, contains more than 1,300 galaxies and lies about 54 million light-years away. The Virgo cluster's gravitational influence extends across tens of millions of light-years, affecting the motions of our Local Group and countless other nearby galaxies. We're falling toward Virgo at several hundred miles per second, drawn by the immense gravitational pull of this cosmic city. The journey will take tens of billions of years, but eventually our Local Group will merge with the Virgo cluster, becoming part of an even larger gravitational structure. Galaxy clusters contain mass equivalent to hundreds of trillions of suns. Yet observations reveal something peculiar. The galaxies within clusters move at velocities approaching millions of miles per hour. These tremendous speeds should have scattered cluster members across cosmic space billions of years ago. The visible matter in cluster galaxies cannot generate enough gravitational force to hold these structures together. Galaxies should fly apart, yet they remain bound. The solution requires invoking dark matter, a mysterious substance that reveals itself only through gravitational effects. Dark matter outweighs visible matter by ratios of about 5:1 throughout the universe. In galaxy clusters, dark matter dominates even more dramatically, sometimes outweighing ordinary matter by factors exceeding 10:1. This invisible material forms the gravitational scaffolding that holds galaxy clusters together despite the tremendous velocities of their member galaxies. We can map dark matter distribution by studying how galaxy clusters bend light from background objects. Massive clusters distort space so severely that they act as cosmic lenses, magnifying and distorting the appearance of galaxies lying far behind them. The amount of distortion reveals how much mass the cluster contains. These gravitational lensing measurements confirm that most cluster mass remains completely invisible, detectable only through its gravitational influence on light and visible matter. The bullet cluster provides perhaps the most spectacular evidence for dark matter's existence. This structure formed when two galaxy clusters collided at speeds exceeding 10 million miles per hour. During the collision, the gas clouds within each cluster interacted and slowed down, while the dark matter components passed through each other largely unaffected. Gravitational lensing maps show the dark matter and visible matter now separated by millions of light years, having been pulled apart by the collision dynamics. This observation proves that invisible mass exists independently of normal matter. Galaxy clusters themselves organize into even larger structures called superclusters. These enormous formations stretch across distances measuring hundreds of millions of light years. Our local group belongs to the Laniakea supercluster, a gravitational collection spanning 520 million light years and containing approximately 100,000 galaxies. The discovery of superclusters revealed that cosmic organization extends to scales far larger than individual galaxy clusters. Superclusters form through gravitational processes operating over billions of years. Dark matter began clumping together shortly after the Big Bang, eventually creating the gravitational wells where galaxies formed. These galactic collections gradually merged into clusters, and clusters organized themselves into superclusters. The largest known supercluster, the Shapley supercluster, contains more than 8,000 galaxies and spans 650 million light-years. Its gravitational influence affects galaxy motions across a significant fraction of the observable universe. Mapping supercluster structure requires measuring distances to millions of galaxies. Recent surveys have revealed that superclusters connect to form a vast, three-dimensional network resembling cosmic webbing. Galaxies arrange themselves along filaments connecting dense nodes where galaxy clusters form. Between these filaments lie enormous voids containing very few galaxies. This cosmic web structure extends throughout the observable universe with remarkable consistency. The cosmic web emerges naturally from gravitational processes. Computer simulations starting with tiny density variations in the early universe automatically produce web-like structures as gravity amplifies these initial irregularities. Dark matter clumps together first, creating gravitational seeds that later attract normal matter. Gas flows along dark matter filaments like water through pipes, feeding galaxy formation in the densest regions where multiple filaments intersect. Individual filaments in the cosmic web stretch across hundreds of millions of light years while maintaining relatively narrow widths of perhaps 20 million light years. These cosmic threads contain enormous amounts of matter, enough to fuel billions of galaxies, yet appear impossibly thin when viewed at universal scales. Galaxy clusters form at intersections where several filaments meet, creating gravitational traffic jams that trap matter for billions of years. The gas threading through cosmic web filaments remains largely invisible to optical telescopes. This warm, hot intergalactic medium reaches temperatures of millions of degrees while maintaining densities barely above perfect vacuum. Detecting this elusive material requires specialized X-ray telescopes capable of registering extremely faint emissions from hot gas. Recent observations have confirmed that this predicted component of the cosmic web actually exists, containing more mass than all the stars in all the galaxies combined. Between the filaments lie cosmic voids, enormous regions containing very few galaxies. These voids occupy roughly 80% of cosmic volume, despite containing less than 15% of universal matter. The Boyer's void, one of the largest known, spans 330 million light-years in diameter while containing fewer than 60 galaxies. If our local group existed within this cosmic desert, the nearest major galaxy would be so distant it would appear as a barely detectable smudge in our most powerful telescopes. Cosmic voids form as natural consequences of web structure. As matter clumps together along filaments and walls, it drains away from the regions that become voids. These empty areas aren't completely devoid of matter. They contain dark matter filaments too tenuous to gravitationally trap normal matter, plus trace amounts of gas at extremely low densities. Galaxies that do form within voids follow different evolutionary paths than galaxies in denser regions, often appearing smaller, bluer, and more actively forming stars. The largest known void, the Giant Void or KBC supervoid, spans approximately 1.8 billion light-years across. If our galaxy existed at its center, we wouldn't have discovered external galaxies until perhaps the 1960s. The night sky would appear almost completely empty beyond our local group. This emptiness would have profoundly affected the development of astronomy and our understanding of cosmic structure. Now picture the entire cosmic web, with its filaments, clusters, walls and voids, all extending throughout space as far as telescopes can observe. This immense structure contains roughly 2 trillion galaxies distributed across observable space. Each galaxy harbors billions or hundreds of billions of stars. Most stars likely host planetary systems. The total number of planets in the observable universe probably exceeds the number of grains of sand on every beach on Earth. 2 trillion galaxies scattered across cosmic space. This number overwhelms human intuition. If you could observe one galaxy per second, counting would require 63,000 years to view them all. These aren't just points of light. Each galaxy represents a massive collection of stars, gas, dust, and dark matter, a cosmic city containing enough raw material to build billions or trillions of planetary systems. Each galaxy hosts its own stellar nurseries where new suns ignite, its own stellar graveyards where massive stars explode, its own central supermassive black hole governing galactic dynamics. Multiplying 2 trillion galaxies by an average of 100 billion stars per galaxy yields a stellar population approaching 10 to the 24th power. This number, one followed by 24 zeros, exceeds the count of sand grains on Earth. Consider that for a moment. More stars exist in the observable universe than grains of sand on every beach, every desert, every ocean floor on our planet. Each of those stars represents a nuclear furnace, potentially hosting an entire planetary system. The probability mathematics becomes staggering. If even 1% of stars host Earth-like worlds in habitable zones, the universe contains tens of billions of potentially habitable planets. Some fraction of these worlds may have developed life. Some fraction of life-bearing worlds might have produced intelligent civilizations. Even using extremely conservative estimates that make life rare and intelligence rarer still, the sheer numbers suggest that we almost certainly aren't alone in the universe. Yet the vast distances separating stars create isolation that may prevent most civilizations from ever communicating. Even traveling at light speed, journeys between stars require years or decades. Conventional spacecraft would need thousands or tens of thousands of years to reach even the nearest stellar neighbors. Radio signals take years to reach nearby stars, centuries to reach most stars in our galaxy, and millions of years to reach other galaxies. Any civilization we might detect through radio astronomy would be showing us their past, not their present. This isolation helps explain why our sky appears so quiet despite the enormous numbers of potential cosmic neighbors. The universe may teem with life and intelligence, yet the fundamental barriers of distance and light speed keep civilizations separated by gulfs too wide for easy communication. We exist in cosmic solitude not because we're alone, but because space is so incomprehensibly vast that even abundant life remains scattered too thinly for easy contact. The 2 trillion galaxies we can observe don't represent the full extent of cosmic structure. These galaxies occupy what astronomers call the observable universe, a sphere of space containing everything from which light has had time to reach Earth since the Big Bang. This observable sphere measures approximately 93 billion light-years in diameter, but the universe certainly extends beyond this horizon. How much farther remains one of cosmology's greatest mysteries. The size of the observable universe exceeds the age of the universe multiplied by the speed of light, because cosmic expansion stretches space itself. Light from the most distant observable objects began its journey 13.8 billion years ago, when the universe was only 380,000 years old. During the journey time, expansion carried the source objects to much greater distances. Objects that emitted light 13.8 billion years ago now lie roughly 46.5 billion light-years away, having been transported to these greater distances by expanding space. This creates one of the most counterintuitive aspects of cosmic observation. The most distant galaxies we see appear as they existed when the universe was young and small. Yet those same galaxies currently exist far beyond our observational horizon, having evolved into forms we cannot observe. We can never see the present state of the most distant observable objects. They exist in our past, but beyond our present cosmic horizon. The edge of the observable universe coincides with the cosmic microwave background, the afterglow from when atoms first formed and space became transparent to light. Before this moment called recombination, the universe remained opaque. Free electrons scattered photons so efficiently that light couldn't travel more than microscopic distances before being absorbed and re-emitted. The universe resembled the interior of a glowing fog bank where nothing could be seen beyond immediate surroundings. When cosmic expansion cooled temperatures below about 3,000 degrees, protons and electrons combined into hydrogen atoms. This removed the free electrons that had been scattering light, and the universe suddenly became transparent. Photons could finally travel freely through space. The radiation released at this moment has been traveling toward us ever since, stretched by cosmic expansion from visible wavelengths into microwave frequencies. We observe this cosmic microwave background arriving from every direction in space with remarkable uniformity. Temperature variations across the sky measure only a few millionths of a degree. These tiny fluctuations represent quantum uncertainties from the universe's birth, amplified by cosmic expansion into the seeds that eventually became galaxies. The cosmic microwave background provides our baby picture of the universe, showing conditions when cosmic time measured only 380,000 years compared to the current age of 13.8 billion years. But this radiation wall marks the absolute limit of electromagnetic observation. No telescope can see beyond the cosmic microwave background because no light existed in observable form before recombination. Earlier cosmic epochs remain hidden behind this curtain of ancient radiation, accessible only through indirect detection methods involving gravitational waves or neutrinos that can pass through the opaque early universe. Beyond the cosmic microwave background lies a realm we know existed, but can never directly observe. Theoretical physics provides glimpses into conditions before the universe became transparent. During the first 380,000 years, temperatures exceeded those in stellar cores. Matter existed as plasma, where atomic nuclei couldn't hold electrons. The entire universe glowed brighter than any star's surface. Even earlier epochs push physics toward its limits. During the first 3 minutes, cosmic temperatures allowed nuclear fusion throughout space. Protons and neutrons combined into light elements, creating the cosmic abundance of hydrogen, helium, and trace amounts of lithium we observe today. This primordial nucleosynthesis occurred when the entire universe was smaller than our current solar system, yet contained all the matter we can observe today. The first second of cosmic existence remains largely mysterious. Theoretical models suggest that fundamental forces separated during this period as expansion cooled the universe below energy scales where particle physics breaks down. Gravity separated first, followed by the strong nuclear force, then electromagnetic and weak nuclear forces. But confirmed observations of this era remain impossible with current technology. Even earlier, during the first tiny fraction of a second, cosmic inflation appears to have expanded space by enormous factors. This exponential expansion stretched quantum fluctuations to cosmic scales while creating space vastly larger than our observable volume. If inflation theories prove correct, our observable universe represents an infinitesimally small portion of total cosmic volume. Scientists using precise measurements of cosmic geometry have calculated that the true universe likely extends far beyond our observable horizon. The observable universe shows no detectable spatial curvature, implying that cosmic space is either perfectly flat or curves so gently that we cannot detect the curvature across our entire observable volume. Flat geometry indicates that the universe extends much farther than we can see, just as Earth's surface appears flat locally despite the planet's overall spherical shape. Conservative estimates based on cosmic flatness suggest the universe measures at least 7 trillion light-years across, roughly 75 times larger than our observable sphere. This minimum estimate means that for every galaxy we can observe, at least 400,000 similar galaxies exist beyond our cosmic horizon. The true extent might be far larger, potentially infinite. Eternal inflation models propose even more extreme possibilities. These theories suggest that new space constantly forms through quantum fluctuations in regions where inflation hasn't ended. This eternal inflation process creates infinite numbers of observable universe-sized bubbles within an ever-expanding cosmic structure. Each bubble would contain its own collection of galaxies isolated from neighboring regions by expansion too rapid for light to bridge. If eternal inflation occurs, then every possible arrangement of matter must occur somewhere within the infinite cosmic structure. Planets identical to Earth would exist in staggering numbers. Civilizations equivalent to human society would develop countless times. Perfect duplicates of our entire observable universe would be repeated throughout infinite space. The probability mathematics of infinity require that every possible configuration occurs, not just once, but infinite times. Yet this vast hidden cosmos remains forever inaccessible to observation or exploration. Even traveling at light speed, explorers could never reach regions beyond our cosmic horizon because expansion carries them away faster than any signal can propagate. The hidden universe represents a realm we can theorize about, but never directly study. Our observable sphere contains less than 1% of cosmic totality if conservative estimates prove correct, potentially far less if eternal inflation occurs. The discovery that we can observe only a tiny fraction of the universe fundamentally changes our perspective on cosmic significance. Every star visible in our night sky, every galaxy observable through our most powerful telescopes, every possible alien civilization within our cosmic horizon, all of it exists within less than 1% of universal content. The remaining 99% or more of existence lies forever beyond human knowledge. Something invisible dominates the universe. Dark energy, comprising roughly 68% of cosmic contents, accelerates the expansion of space with a force so powerful it overwhelms gravity across distances larger than galaxy clusters. This mysterious component pushes distant galaxies away from us at ever-increasing speeds. Its discovery shocked astronomers who expected gravitational forces to gradually slow universal expansion. In 1998, two independent research teams studying distant supernovae found that cosmic expansion was speeding up rather than slowing down. This observation contradicted all predictions. Gravity should pull matter together, slowing expansion over time. Instead, measurements showed expansion rates increasing. This discovery earned the 2011 Nobel Prize in Physics and revealed that most of the universe consists of something we don't understand. Dark energy behaves unlike anything else in nature. Normal matter becomes less dense as space expands. Pack galaxies into a smaller volume and density increases. Expand space and density decreases. But dark energy maintains constant density as the universe grows. Double the volume of space and dark energy doubles in total amount while maintaining the same density everywhere. This unusual property means dark energy's influence grows stronger over time as space expands. Current expansion rates indicate space roughly doubles in size every 10 billion years. This seems gradual until you consider that dark energy's constant density means its gravitational repulsion doubles whenever space doubles. Cosmic acceleration therefore increases exponentially, creating runaway expansion that will eventually overcome all other forces in the universe. Observations show that dark energy currently dominates cosmic dynamics at scales larger than several 100 million light-years. Within smaller distances, gravitational attraction between matter concentrations can overcome dark energy repulsion. Galaxies within our local group remain gravitationally bound despite cosmic expansion, but galaxies beyond our immediate neighborhood are being carried away by dark energy at speeds that will eventually exceed light velocity. This cosmic tug-of-war determines the fate of every galaxy we observe. Most cosmic neighbors will disappear beyond our observational horizon within a few trillion years. Galaxies currently within our observable sphere will cross permanently beyond reach as accelerating expansion carries them into regions where space expands faster than light. Future astronomers will inhabit an increasingly empty cosmos. The nature of dark energy remains profoundly mysterious. Leading theories suggest it represents vacuum energy arising from quantum fluctuations in empty space. Quantum mechanics predicts that vacuum contains constantly appearing and disappearing virtual particles. These quantum fluctuations might generate a baseline energy density throughout space. The problem is that theoretical calculations predict vacuum energy densities exceeding observations by factors of 10 to the 120 power, making this the worst prediction in physics history. Alternative theories propose that dark energy varies over time, or that gravity behaves differently at cosmic scales. Modified gravity theories suggest that Einstein's general relativity requires adjustments when applied across billions of light-years. Perhaps gravity weakens at extreme distances, creating an apparent acceleration without requiring dark energy. But observations so far support standard general relativity across all tested scales. Some theoretical calculations suggest that dark energy acceleration will continue increasing until it tears apart every bound structure in the universe. This Big Rip scenario would begin by separating galaxies from clusters, then stars from galaxies, then planets from stars, then molecules from each other, and finally atomic nuclei would be ripped apart. This cosmic destruction would occur roughly 22 billion years from now if current acceleration trends continue increasing. But less extreme models suggest dark energy might remain constant or even decrease over cosmic time. These possibilities would prevent the Big Rip while still isolating distant galaxies beyond observational reach. Current observations cannot yet distinguish between these scenarios. We know dark energy dominates the universe, but we don't know whether its strength changes over cosmic time. Dark energy's existence means we live during a temporary golden age of cosmic visibility. The observable universe currently contains more galaxies than at any previous time in cosmic history. Young universes were smaller with fewer galaxies within observable range. Future universes will see galaxies disappear as expansion carries them beyond cosmic horizons. We occupy a special moment in cosmic time when maximum cosmic structure remains visible. Within 50 billion years, the Virgo cluster will cross our cosmic horizon, becoming permanently unobservable. The most distant galaxies we currently detect will fade as their light becomes too redshifted to observe. Within 100 billion years, only local group galaxies will remain visible to observers in our cosmic neighborhood. The night sky will appear almost empty except for our merged Milky galaxy. Future astronomers living billions of years from now may have no evidence that external galaxies ever existed. The expansion history of the universe will be erased from observational records. The Big Bang theory might never be discovered because the evidence will have vanished. We are fortunate to exist when cosmic history remains visible, when distant galaxies still populate our telescopes, when the universe reveals its true scale. Yet even our privileged view shows us less than 1% of cosmic reality. Most of the universe has already expanded beyond our observational reach. Dark energy ensures that this cosmic isolation will only increase with time. We observe a universe that is simultaneously vast beyond comprehension and represents only the tiniest fraction of total existence. You currently occupy one planet orbiting one star in one galaxy among 2 trillion observable galactic systems scattered throughout a cosmic volume that might represent less than 1% of universal totality. This perspective places human existence within a context that should fundamentally alter every assumption about significance and importance. Earth measures 25,000 miles in circumference, a small sphere of rock and metal spinning through space at 67,000 miles per hour around a stellar furnace that consumes 4 million tons of matter every second. Our Sun represents a perfectly average star, neither especially large nor particularly small, burning at moderate temperatures compared to the hottest blue giants or coolest red dwarfs. Among the hundreds of billions of stars in our galaxy, Sol would draw no special attention from alien astronomers. The Milky Way itself ranks as an ordinary spiral galaxy, neither among the largest ellipticals containing trillions of stars, nor among the smallest dwarfs harboring only millions of stellar furnaces. Yet from this unremarkable rock orbiting an average star in a typical galaxy, conscious beings emerged who can contemplate cosmic scales spanning billions of light years. Humanity developed from simple chemical processes on one small planet. We evolved to hunt and gather on African plains. Our brains developed to track prey animals, recognize edible plants, and navigate social relationships within small tribal groups. Nothing in our evolutionary history prepared us for understanding galaxies or cosmic expansion or the vast scales of space and time. Yet here we are, temporary patterns of organized matter that somehow achieved the remarkable ability to study the universe itself. We've mapped galaxies across billions of light years. We've detected gravitational waves from colliding black holes. We've discovered planets orbiting distant stars. We've measured the age of the universe and traced cosmic evolution from the Big Bang to present structures. The same cosmic processes that created galaxies, stars, and planets also created the chemistry that led to life and consciousness. Every atom in your body except hydrogen was forged inside a star that lived and died before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created through nuclear fusion in stellar cores billions of years ago. When massive stars exhausted their fuel and exploded as supernovae, they scattered these heavy elements through space. This enriched material eventually collected into new solar systems, including ours. We are literally made of stardust, matter forged in cosmic furnaces and assembled into living forms. This material connection links humanity to cosmic evolution across billions of years. We represent the universe becoming aware of itself, matter achieving consciousness, and studying its own origins. Despite occupying one tiny corner of an incomprehensibly vast cosmos, humans have discovered fundamental truths about reality that apply across cosmic scales. We've glimpsed the true size of existence and found ourselves simultaneously insignificant and profoundly meaningful. The cosmic perspective reveals human existence as both infinitesimally small and remarkably important. Small because we occupy one planet among potentially trillions of habitable worlds, orbiting one star among hundreds of billions, in one galaxy among trillions, within an observable universe that represents perhaps less than 1% of cosmic totality. But important because we represent one of the universe's ways of knowing itself. Through human consciousness, the cosmos examines its own structure and evolution. We exist during a remarkable moment in cosmic time, early enough that stars still burn brightly and galaxies remain visible across cosmic distances, late enough that heavy elements exist to build rocky planets and complex chemistry. We live when the universe is neither too young to have developed interesting structures, nor so old that cosmic expansion has isolated everything, beyond detection. The current era may represent peak cosmic complexity, the time when the universe achieves maximum organization before expansion disperses everything. The scales we've explored, from our cosmic neighborhood to the limits of observation, reveal a universe far stranger and more magnificent than previous generations imagined. Ancient humans believed the stars were holes in a celestial sphere, or perhaps distant fires. Medieval astronomers thought the universe extended only to Saturn's orbit, with everything else existing in a heavenly realm beyond physical space. Even early 20th century astronomers believed the Milky Way comprised the entire universe, with nothing existing beyond our galactic boundaries. Each expansion of human knowledge revealed larger cosmic scales. The discovery of stellar distances showed that space extended far beyond the solar system. The discovery of galactic distances proved that our Milky Way represented just one island among many. The discovery of cosmic expansion demonstrated that space itself grows, carrying galaxies apart through a process no one anticipated. And now we know that even the vast observable universe likely represents only a tiny fraction of total cosmic existence. Yet mysteries remain. We don't know what dark matter is beyond its gravitational effects. We don't know what dark energy is or why it has the strength we measure. We don't know if the universe is truly infinite or merely very large. We don't know if parallel universes exist or if eternal inflation continues creating infinite new cosmic volumes. We don't know if consciousness exists elsewhere or if life represents a rare cosmic accident. We don't know if the laws of physics remain constant throughout cosmic space or vary in distant domains beyond our observation. These unanswered questions make the universe even more fascinating. Despite everything we've discovered, despite mapping galaxies across billions of light years and tracing cosmic evolution back to the Big Bang, we've barely begun understanding ultimate reality. The known universe already exceeds human comprehension. The unknown universe may dwarf the known by factors that make our current observations look like examining a single grain of sand while an entire beach remains unexplored. Future observations will reveal more cosmic detail. Better telescopes will detect fainter galaxies at greater distances. Improved instruments will probe the cosmic microwave background for subtle patterns revealing conditions from cosmic inflation. Gravitational wave detectors will observe colliding black holes and neutron stars across cosmic time. New particle accelerators might discover dark matter particles or reveal new physics beyond current theories. Each advance will answer some questions while raising new mysteries. But some cosmic truths remain permanently beyond observation. We can never see beyond the cosmic microwave background using electromagnetic radiation. You are sitting on a rock hurtling through space, orbiting a nuclear furnace in a galaxy among trillions, within an observable universe that might represent less than 1% of reality. This remains true regardless of what you do next. But you are also a conscious being capable of understanding. This cosmic context, capable of contemplating scales far beyond immediate experience, capable of finding meaning within immensity. And that makes you, however small, however temporary, genuinely remarkable in ways that scale alone cannot measure. We can never observe regions of space whose light will never reach us, no matter how long we wait. Entire cosmic domains may exist beyond our horizon, governed by physics we cannot verify, populated by structures we will never detect. We can theorize, simulate, and infer their properties, but they will remain permanently beyond direct confirmation. Our understanding of reality is therefore bounded not just by technology, but by fundamental limits of space-time itself. Cosmic humility comes not from weakness, but from perspective. Recognizing our limits does not diminish our worth, it refines it. Intelligence thrives not by knowing everything, but by understanding that there will always be more to know. Curiosity is humanity's superpower, the one force capable of leaping across light years without moving an inch. Even if future observers lose access to visible galaxies, they may still rediscover cosmic truths through mathematics, inference, or relic radiation. Knowledge may vanish from the sky, but it need not vanish from the mind. This is why your existence matters. You are part of a rare generation born at the only time in cosmic history when the universe's past, present, and future are all visible at once. You were born in an era when humans can watch galaxies form, stars die, planets emerge, and black holes collide, all from one small world. You were given sight into creation itself. To waste such an opportunity on triviality would be the true cosmic tragedy. And yet meaning is not granted by the universe. It is forged within it. The cosmos does not care whether you understand it, but your ability to understand it gives you power beyond measure. You will one day return to silence, your atoms scattered among the stars that once created them. But the universe will be forever altered by the brief moment when those atoms asked where they came from. You are not merely in the universe, you are of the universe. You are a fragment of space-time experiencing itself. You are a temporary arrangement of particles that develop the audacity to comprehend galaxies. The universe spent 13.8 billion years preparing the conditions for you to exist. Now that you do, the only remaining question is what you choose to do with that awareness. Will you live as if you are small, or as if you are rare? Because you are both. Perhaps the greatest realization is that significance is not measured by size or duration, but by awareness. A galaxy can burn for trillions of years and never once question its purpose. A star can forge gold in its core and scatter it across space without ever knowing what it has done. But you, fragile, temporary, infinitesimal you, can look across billions of light years and ask why. You can experience awe. You can feel humility in the face of eternity and still choose to act with intention. No supernova has ever written a poem. No black hole has ever felt regret. No nebula has ever wondered whether kindness matters. Yet you can. You, a self-aware collection of atoms arranged in the shape of a human being, possess something that even the most powerful forces in nature lack: the ability to care, to choose, to love, to seek meaning in a universe that offers none by default. That ability alone makes you more extraordinary than any supercluster of galaxies. The universe can create stars by accident, but it can only create purpose through minds capable of recognizing their own existence. And now that you recognize yours, the only real question left is not whether you matter, but what you will do with the brief and astonishing moment in cosmic history when you were alive to witness it. Perhaps the greatest realization is that significance is not measured by size or duration, but by awareness. A galaxy can burn for trillions of years and never once question its purpose. A star can forge gold in its core and scatter it across space without ever knowing what it has done. But you, fragile, temporary, infinitesimal you, can look across billions of light years and ask why. You can experience awe. You can feel humility in the face of eternity and still choose to act with intention. No supernova has ever written a poem. No black hole has ever felt regret. No nebula has ever wondered whether kindness matters. Yet you can. You, a self-aware collection of atoms arranged in the shape of a human being, possess something that even the most powerful forces in nature lack: the ability to care, to choose, to love, to seek meaning in a universe that offers none by default. That ability alone makes you more extraordinary than any supercluster of galaxies. The universe can create stars by accident, but it can only create purpose through minds capable of recognizing their own existence. And now that you recognize yours, the only real question left is not whether you matter, but what you will do with the brief and astonishing moment in cosmic history when you were alive to witness it. And if all of this still feels distant, if galaxies and light years and cosmic horizons seem too abstract to matter in the rhythm of your daily life, then bring it closer. Consider that every smile you cause, every hand you steady, every moment you choose patience over anger or understanding over judgment creates a tiny but real alteration in the fabric of reality. Physicists call it entropy when systems fall apart, when order decays into disorder. But human beings possess the rare ability to reverse entropy in places where it matters most, inside each other. A kind word can stabilize a crumbling mind. A moment of empathy can redirect the course of a life. A loving decision can ripple through descendants not yet born. In a universe where gravity pulls everything apart and time guarantees eventual silence, compassion becomes rebellion. Hope becomes defiance. Choosing to care becomes the most scientifically improbable act of all, because it is not required by physics or chemistry or evolution. It is chosen freely by consciousness. And that means that no matter how vast or uncaring the cosmos may seem, the most meaningful forces in existence are not the ones written in equations, but the ones you decide to create. So let the universe remain vast. Let the stars burn and galaxies collide. Let expansion continue until all horizons fade. But while you are here, while your thoughts still cohere and your heart still beats, choose to be something the universe cannot erase. A source of warmth in the cold, light in the dark, and will in a realm ruled by inevitability. So let this be your final reminder, not a command, not a sermon, not a demand shouted by a universe that does not speak, but a quiet offering from one moment of awareness to another. You were given a life that statistically should not exist. You are an unthinkable anomaly in a cosmos that prefers silence. Stars do not think. Nebulae do not feel. Galaxies do not worry about purpose. But you do. You wake each morning knowing that time is limited. You walk through your days with the faint weight of mortality always pressing gently against your spine. You fall asleep every night not knowing if you will ever open your eyes again. And still, you hope. You plan. You love. You forgive. You imagine futures that haven't happened yet. You recall pasts that no longer exist. You sit in rooms made of stardust and talk to other stardust beings about dreams and fears and memories and meaning, as if such fragile things were more important than the fusion of suns. And maybe they are. Maybe the greatest accomplishment of the universe is not that it forged black holes or stretched itself across trillions of light years, but that somewhere, in one small corner of one average galaxy, a tiny collection of atoms arranged into a human brain felt something when it saw the night sky. Perhaps that feeling, that moment of awareness, that breath caught between insignificance and wonder, is the highest form of order reality has ever constructed. And if that is true, then your task is not to be perfect, immortal, or legendary. Your task is simply to remain aware, to be present, to carry your brief existence with sincerity, to look at the world around you, whether that world is a sprawling city, or a quiet room, or the vast universe stretching overhead, and whisper, not in fear, but in recognition, "I see you. I know that you will outlast me. But while I am here, I will respond not with despair, but with curiosity. Not with apathy, but with participation. Not with fear, but with reverence. Because one day your atoms will scatter and your name will fade, and the universe will continue as if you had never existed. But for this moment, you do exist. And that makes all the difference. For however long you remain assembled into the shape called you, let the universe know that you noticed.